Hey guys, what's up? Welcome back. We are on chapter 15 still, double integrals, and today is going to be section 15.4, which is applications of double integrals. Hopefully you've been going on your homework. Things are going well, I think. Getting ready for the second exam coming up in 1 week. So yeah, just about through with chapter 15. We have 3 sections left after today. So yeah, hopefully things are going well. 15.4 today, applications of double integrals. So applications of double integrals. And we're going to mostly talk about applications of like mass, center of mass, moments of inertia, stuff like that. But there's also an application to probability theory. So I'll just mention that at the very end. I won't do too much with it, but just throwing that out there. So when I say the setup is going to be a certain setup, it doesn't mean this is the only setup. It's just the setup we're going to focus on. The setup is lamina properties. So the setup for today is supposing we have a thin, flat plate, sometimes called a lamina. So something like this. And so basically in the X and Y direction, you kind of see the solid, but in the Z direction, there's not much thickness to it. So it's thin in the Z direction. So really it only depends on X and Y. And then there's a density, rho of XY, that is kilograms per meter squared, because the thickness, again, is negligible or irrelevant. So the density rho of XY is an areal density, or it only depends on the area, mass per unit area. So then the total mass of the lamina M would be the sum over the whole region R that is occupied by the lamina. The sum over the region R, rho of XY dA. Think about this. You have your lamina in the XY direction. And you want to find the mass of that lamina. Well, you break it up into a bunch of little rectangles. Find the density at the point in the rectangle, multiply it by the area of that rectangle. And you get the mass of that rectangle. Add those all together over the whole region. That's the very definition of an integral. So that's going to be our setup. So that's the total mass of the lamina. And then the center of mass, is point X bar, Y bar, where X bar is equal to double integral over the region R, X times rho of XY dA over total mass, and Y bar is equal to double integral over the region R, Y times rho of XY dA over the total mass. And sometimes people call this M sub y over M sub x over m. But the lettering is backwards on those two. So this double integral is called M sub y. This double integral is called M sub x. And these are what you call the first moments. So, first moments. And then the total mass is in the denominator. So what is going on here with the center of mass calculations? Well, the center of mass is the balance point for the lamina. So you basically take the x weighted average divided by the total mass, and that gives you the x location for the center of mass. Same thing for y bar. You take the y weighted average of the mass divided by the total mass, and you get the y location for the center of mass. So it depends on the distribution of the mass, and it also depends on the shape of the mass. So that's the center of mass calculation, x bar, y bar. So this is basically the balance point for the lamina. So the center of mass is the balance point of the lamina. So if you were to basically take the lamina and try to find one point where you could stick a needle, maybe right there, that would be your center of mass. So where could we balance the lamina by placing a needle? And so that's what this point x bar, y bar represents. You're basically taking a weighted average in the x direction of the mass and a weighted average in the y direction of the mass, and dividing by the total mass in each case, and you get the center of mass. Any questions so far about the setup? Okay, then let's look at an example. Example is find the center of mass. So find the center of mass of the lamina in the shape of the region bounded by the graphs y equals x squared and y equals 4. having mass density given by rho of xy equals 1 plus 2y plus 6x squared. So we have a lamina here. It has a certain density function, and we're going to find the center of mass, the balance point for this lamina. So I guess first thing we'll do is graph the region. So the lamina looks like this. We have y equals 4 and y equals x squared. And the lamina is everything inside there. And there's some kind of negligible thickness kind of going in and out of the screen. But the xy direction looks like this. So that's our lamina. Okay. Now, just because the lamina is symmetric doesn't necessarily mean the center mass will be symmetric. That depends on the density function. But we notice the density function here is symmetric in the x direction. So note, rho of xy has symmetry in the x axis. So what you do on one side, you'll get the same thing on the other side of the x direction. So the density is small along the y-axis, but then it's really large out here at these corners. So there's a lot of mass out here. But there's the same amount of mass on both sides. So we anticipate x bar to be 0 at that point. So we anticipate x bar will equal 0. And that'll just be a sanity check for us whenever we do the actual computation. The y bar looks like as we move up, there's more mass as we move up the lamina. So probably like there's a lot of mass up here and a very little bit of mass down here. So it's like a non-uniform solid. So I anticipate the center of mass will be somewhere up along the y-axis right around here. So somewhere up there is where we anticipate the center of mass to be. So how do we calculate the center mass? Well, we go through and just do the computation. So the mass M is going to be the double integral over the region R, rho of xy dA, which is going to be, well, I have to find the bounds for this region. So let's find the bounds. Let's see. I set it up maybe as like type 1 bounds. So this is 2, this is -2. Since y is equal to 4, that's 4 equals x squared, so x equals plus minus 2. So that's where those two graphs intersect. And then y is going to go from x squared to 4. So -2 less than or equal to x less than or equal to 2, and then x squared less than or equal to y less than or equal to 4. So those are our type 1 bounds. So we've got our bounds, now we can do our double integral to get the mass. Integral from -2 to 2, integral from x squared to 4, 1 plus 6y plus, whoops, I think it was 2y. 1 plus 2y plus 6x squared dy dx. And this will give us the total mass of our lamina. So this is going to be the integral from -2 to 2. Integrate with respect to y, we get y plus y squared plus 6x squared y from x squared to 4 dx. And that's going to be integral from -2 to 2. Plug in the bounds, we get 4 plus 16 plus 24x squared minus x squared minus x to the 4 minus 6x squared x squared dx. And I'm going to simplify that. Integral -2 to 2, 20. So we got 24 minus 1 is 23 minus 23 x squared minus 7 x to the 4 dx. Oh, that should be plus 23. And now this is an even function over symmetric interval. So even function symmetric interval. So what we're going to do is change it to be 2 times integral from 0 to 2, 20 plus 23 x cubed squared minus 7x to the 4 dx. Now I can integrate pretty easily. 2 times 20x plus 23 over 3 x cubed minus 7 over 5 x to the 5th from 0 to 2. And plugging in the bounds, we get 2 times, let's see, that'd be 40 plus 23 over 3 times 8 minus 7 over 5 times 32. And I do believe that that comes out to be 1696 over 15. So that's the total mass of the lamina. Any questions so far? Okay, now to get x bar, we know x bar is equal to m sub y over m. Well, we have m, now we just need m sub y. So m sub y is the double integral over the region x times rho of xy dA. So this is going to be integral from -2 to 2, integral from x squared to 4, x times 1 plus 2y plus 6x squared dy dx. So actually, what we can do is pull out the x from here and just do the y integral. So I can move that x out since it has nothing to do with y. So this is going to be integral from -2 to 2 x times, and then integrate with respect to y. So we get y plus y squared plus 6x squared y from x squared to 4 dx, which is exactly what we had earlier. So it's really just going to be integral from -2 to 2 x times what we had earlier, which was 20 plus 23x squared minus 7x to the 4 dx. And we multiply by x, we're going to get integral from -2 to 2, 20x plus 23x cubed minus 7x to the 5th dx. Okay, but now this is an odd function over symmetric interval. So odd function over a symmetric interval. So this thing is going to equal 0. So that tells me that x bar is going to equal 0 over 1696 over 15, which is 0, as we expected. Any questions? You actually might ask yourself, why does x bar go with M sub y? Well, the M sub y notation is kind of saying, how is this distributed about the y-axis? Well, if you want to think about it being distributed about the y-axis, that means in the x direction, because the y-axis kind of splits the x direction into two pieces. So if you're saying the moment about the y-axis, you're basically thinking, okay, how is it distributed along the x direction, because I want to look at the y-axis. Same thing if you want to think about it distributed along the, or about the x-axis, you have to look at the y direction, because the x-axis splits the y direction into two pieces. So you could think of it almost like rotation, but it's not the moment of inertia. We'll get that in a minute. All right, so we've got our y bar calculation still to go. And let's do that one. So y bar, we know, is going to be m sub x over m. And so we've got to get m sub x, which is going to be integral from minus 2, positive 2, integral from x squared to 4 y times 1 plus 2y plus 6x squared dy dx. And on this one, we actually have to do the calculation or the multiplication of y first, because we're integrating y first. So this is going to be integral from minus 2 to 2, integral from x squared to 4, y plus 2y squared plus 6x squared y dy dx. So we distribute that y, and now we can integrate. So this is going to be integral from negative 2 to 2, integrate with respect to y. So we get y squared over 2 plus 2 over 3 y cubed plus 3x squared y squared from x squared to 4 dx. And distribute those, or plug in the bounds. This becomes integral from -2 to 2. And we get 16 over 2, which is 8, plus 2/3 times 64, plus 16 times 3 is 48, so 48x squared, minus x squared squared is x to the 4 over 2, minus 2/3 x squared cubed is x to the 6, plus 3x to the 6 dx. And we can combine the last two terms. And we can integrate after that. So integral from -2 to 2, 8 plus 2/3 times 64. Let's see, 64 times 2 is 128. So 128 over 3 plus 48x squared minus x to the 4 over 2. Let's see, 3 be 9 minus 2 is 7/3, so plus 7/3 x to the 6 dx. And I guess I could technically combine the first two into a single constant, but let's see, is this an even function? It is an even function. So because it's even over symmetric interval, even function over symmetric interval, we can change it to be 2 times integral from 0 to 2. So 2 times integral 0 to 2. And I guess I'll combine that. So that'll be 24 plus 128. So it'll be 152 over 3. Is that right? 24 plus 28. Yep. So 152 over 3 plus 48 over, well no, just 48x squared minus x to the 4 over 2 plus 7/3 x to the 6 dx. And now integrating, we get 2 times 152 over 3 times x plus 16x cubed minus x to the 5th over 10 plus 1/3 x to the 7 from 0 to 2. And this is going to be 2 times 152 over 3 times 2 plus 16 times 8 minus 32 over 10 plus 1/3 times 128. I think if you number crunch that out, I just verify, but I think you get 11,136 over 35. Now see if we have any questions. I'll double check that really fast, but while we wait, I'll see if you guys have questions. Okay. Just gonna double check some things here. Because this number is different. So actually, what I got from doing this number was 2688 over 5. So I think I made a mistake somewhere. So I think the correct answer should be 11,136 over 35. And that is not what this number comes out to be. So I've made a mistake somewhere. Let me just double check. Y squared over 2 plus 2/3 y cubed plus 3x squared y squared. Plugging in bounds is 16 over 2, which is 8. 2/3 times 64. And let's see, 3 times 16, which is 48. Minus x to the 4 over 2. Minus 2/3 x to the 6th plus 3x to the 6th. So yeah. Let me double check one more thing. Yeah, I seem to have made a mistake somewhere, but this number is the right y bar, or sorry, the right m sub x. Not sure why I made a mistake. I'll look back through it in a second. So then from here we get y bar equal to 11,136 over 35 times 1 over m, which would equal 11,136 over 35 times reciprocal of m would be 15 over 1696. And that's about 2.8. And that makes sense. So our y value is a little bit more than halfway up the lamina. So if we go back to the picture of our lamina, it makes sense. We thought our y bar would be closer to the top of the lamina because there's more mass at the top of the lamina based on our density function. This y value, this 2y right here, means that as y gets larger, the mass gets larger. The x is symmetric on both sides, so that's why x bar was 0. So now, how did I forget or miss this computation? What did I mess up? Distributed the y. Two y squared, 6x squared y. And y squared over 2, 2/3 y cubed, 3x squared y squared. Plug in, 16 over 2 is 8. 2/3 times 4 cubed, 64. And then 3 times 16, just 48, x squared. Minus x to the 4 over 2 minus 2/3 x to the 6th plus 3 times x to the 6th. Eight plus 128 over 3 plus 48x squared minus x to the 4 over 2. Minus 2/3 plus 3, which is 7/3 x to the 6th. Wait, why is that not a minus? This should be a minus sign here. There we go. Minus here. So this should not be 7/3. It should be minus 11/3. There we go. Negative 11/3 right here. And this should be negative 11 over 21. And so this should be negative 11 over 21. There we go. Now I think that will fix our mistake. There we go. Just double check. 152 over 3 times 2 plus 16 times 8 minus 3 over 10 minus 11 over 21 times 128 times 2. Closer. See if I type that in wrong. It should be 32 over 10. Yeah. There we go. That's it. Okay, good to go. Sorry about that mistake there. We're good to go now. This is indeed the correct number. All right, we're good. So let me just highlight what was wrong. This negative kind of messed us up. I dropped that negative. And so all these are changing. All right, so now what can we do after this? Well, we can calculate something called the second moments. So now second moments. And those are called the mass moments of inertia. mass moments of inertia is the, I guess you could say, the difficulty. How difficult is it to get an object moving around a certain axis or a certain direction? So how difficult or easy is it to rotate an object about a given axis? So that is what we call the mass moment of inertia. The higher the moment of inertia, the more difficult it is to make this object rotate around that axis. So if you think about a solid cylinder, then you have an axis this way. And so this moment of inertia would be really low. Low moment, mass, moment of inertia. If it's a nice uniform density. So making it rotate around its axis of symmetry, easy. Making it rotate around something like this, it's more difficult. So high inertia, low inertia in the green direction, high inertia in the orange direction. So the moment of inertia about the x-axis, moment of inertia about the x-axis is I sub x equal to, again, this is going to play into how's the mass distributed in the y direction. So double integral over r y squared rho of xy dA. And the moment of inertia about the y-axis is going to be concerned with how is the mass distributed in the x direction. So I sub y is going to be double integral over r x squared rho of xy dA. So for that cylinder, we could see there's a lot of mass distributed around the y-axis. So in the x direction, there's mass farther and farther away from the y-axis, so that's a higher moment of inertia. Whereas for the x-axis, the mass is kind of nice and concentrated close to the x-axis. So the closer you are to the axis, the easier it's going to be to rotate that thing around that axis. So those are your mass moments of inertia, or your second moments. Second moments of the object, also called the mass moments of inertia. And example, well, I should say moment of inertia about the origin. That's, I like to call it IO equals double integral over r x squared plus y squared rho of xy dA. So it's the moment about the origin. And it's basically what's the distance to the origin? Well, x squared plus y squared is the distance to the origin. So you're rotating basically in a circle around the origin. So you could think of that as like going this way. If you were to try to spin it around the origin, not the x-axis or y-axis, but just basically around the z-axis. Any questions about that setup? Or what those mean? All right, let's look at an example. Basically the same setup we had earlier for our example, but now just calculate the second moments. So example, find the moments of inertia for the lamina bounded by y equals x squared, y equals 4, with density rho of xy equals 1 plus 2y plus 6x squared. And when I say moments of inertia, I mean x, y, and, or sorry, ix and iy. Your homework will specifically tell you to find the moment of inertia about the origin. But when we say moments of inertia, we mean ix and iy, the second moments. If you want the moment about the origin, it'll explicitly state, find the moments about the origin as well. All right, so what do? We already know the bounds. We got to calculate I sub x, which is going to be double integral over the region y squared rho of xy dA, which is integral -2 to 2, integral x squared to 4, y squared times 1 plus 2y plus 6x squared dy dx. Distribute that and integrate. We get -2 to 2, y cubed over 3 plus 1/2 y to the 4 plus, see, 6 over 3 was 2x squared y cubed from y equals x squared to y equals 4 dx. It's going to be integral -2 to 2, 64 over 3 plus 216 over 2 plus 2 times x cubed, or sorry, x squared times 64 minus x to the 6 over 3 minus 1/2 x to the 8 minus 2 times x to the 8. Don't forget the minus sign this time. dx. And maybe we can simplify that. 216 over 2. Whoops, I said 216. It should be 256. So that's 128 plus 64 over 3. So that's integral -2 to 2, 448 over 3 plus 128 x squared minus x to the 6th over 3 minus 5/2 x to the 8 dx. And this is even over a symmetric interval. So we can do 2 times integral from 0 to 2. So this is 2 times integral 0 to 2. 448 over 3 plus 128 x to the second minus x to the sixth over 3 minus 5 halves x to the 8th dx. And that's going to be 2 times 448 over 3 times x plus 128 over 3 times x cubed minus x to the 7 over 21 minus 5 halves x to the 9 over 9 from 0 to 2. And I do believe if we number crunch that, let's see, what are we going to get? 2 times 448 over 3 times 2 plus 128 over 3 times 8 minus 128 over 21 minus 5 times 512 over 18. And let's see what that's going to be. 448 times 2 over 3 plus 128 times 8 over 3 minus 128 over 21 minus 5 times 512 over 18. All of that times 2. Yes, and we get 61,952 over 63, which is about 983.37. And that looks like a pretty big number, but we need to kind of compare it to something. So we'll compare it to I sub y to see which one's larger. My guess is the x-axis is going to have a larger moment of inertia. The y-axis doesn't feel like it's going to have a very large moment of inertia, not compared to the x-axis, because the mass around the y-axis is symmetric. So let's look at I sub y now. I sub y is going to be integral minus 2 to 2, integral x squared to 4, x squared times 1 plus 2y plus 6x squared dy dx. Again, we can do the same trick where we don't multiply by x squared yet. Just keep it off to the side, x squared, integrate, and we get the same thing that we had last time we integrated this, which was, I'm trying to remember, something like 20. Yeah, 20 plus 23 x squared minus 7 x to the 4 dx. And that's going to be integral 0 to 2, well, negative 2 to 2, 20x squared plus 23x to the 4 minus 7x to the 6 dx. Now use the symmetric interval even function property, so 2 times integral 0 to 2, 20x squared plus 23 x to the 4 minus 7x to the 6 dx. So that's going to be 2 times 20 over 3 x cubed plus 23 over 5 x to the 5th minus x to the 7 from 0 to 2. That's going to be 2 times 20 over 3 times 8 plus 23 over 5 times 32 minus 128. And let's see what that's going to be. 20 times 8 over 3 plus 23 times 32 over 5 minus 128. Multiply that by 2. And we get 2176 over 15, which is about 145.07. So the moment of inertia around the x-axis is much larger. So Ix is much, much larger than Iy, which means more difficult to rotate or stop rotating, if already, around the x-axis. And we can think about this, from a physical standpoint. We had our lamina like that, and it's much harder to rotate it around the x-axis versus the y-axis. Because of the mass distribution. So that's what these numbers Ix and Iy tell us. In this case, Ix is like 8 times larger, roughly, maybe 7 times larger than Iy. So that means it's much harder to start rotating this thing around the x-axis than it is to start rotating it around the y-axis. And vice versa. I mean, if it were already rotating, it would be much harder to stop it from rotating around the x-axis than it would be to stop it from rotating around the y-axis. All right, so that's quite a bit of, I guess, just engineering applications, but then there are also other applications to probability. So other applications of double integrals. We're not going to do any examples, but just want to throw these out there. Other applications of double integrals would include, you could say, if f of xy is a probability density function, and it's actually a joint probability density function, that depends on 2 random variables, x and y. Then probability x is between a and b, and y is between c and d, is equal to the double integral from a to b for x, integral from c to d for y, f of xy dy dx. And integral over the whole real space, R2, f of xy dA equals 1, and f of xy is greater or equal to 0 for all xy. So it's just the same properties we know a probability density function should satisfy. So this would be a probability application of double integrals. Whoops, sorry. Another application is to physics, electrostatics. If, we'll call it rho of xy, so this is like our first application. Second application, if rho of xy is the amount of charge in coulombs, per unit area on a lamina, then the total charge on a plate is Q equal to double integral over the region R rho of xy dA. So it's a non-uniform charge density function. So that's another way we could calculate this. That's something else we could calculate with the double integral. So two more applications, not just, you know, statics engineering stuff, but also probability and then physics, electrostatics. So what you're calculating with an integral is all about what the function you're integrating represents. Once you know what the function you're integrating represents, you can know what you're actually calculating with the double integral, triple integral, whatever kind of integral you're talking about. So that's the general idea. Hopefully this helps a little bit kind of clear up any, you know, theoretical confusion of what a double integral might mean in the real world. But yeah. Any questions? If not, I'll see you guys next time. Have a good one. Talk to you later.